Welcome friends to this new lecture of soil science and technology, and in this lecture we will try to finish the soil temperature which we started in our last lecture, and we will also try to solve several couple of problems related to soil aeration and soil temperature. So, in the soil temperature we discuss about how soil temperature is affecting different soil as well as microbial and other processes. So, let us see some other examples. So, let us see what is the implication of soil temperature in soil heating by fire. Well, remember that when heating up the surface soil to remove the volatile organic carbons in sandy soil, and as a result of heating up of the surface, so as a result of the heating up of surface soil, the volatile organic compounds diffuses, the volatile organic compound diffuses to the subsoil and get there solidified. So, you can see that this is a burning of plant litter at the surface. So, this is the reason, and as a result of that soil temperature increases with the soil temperature the soil temperature increases, and as a result of that whatever volatile compounds are there at the top of the surface, they will diffuse to the subsoil and again solidified. So, obviously because of there is a temperature gradient from surface soil to the subsurface soil, as you can see here. So, this volatile substance will diffuse into the subsoil and again solidified, and it will drastically reduce the infiltration of the soil because they are water repellent in nature. So, that is how soil temperature by forest fire affects the soil water movement as well as different other soil physical and chemical properties. So, let us move to the next slide and see what are the important thermal properties of the soil. So, we all know heat capacity. So, what is the specific heat of soil? Now, specific heat of the soil is the heat capacity per gram of soil, which is measured in terms of calorie per gram, and it controls the degree to which the soil warms up. I am sorry, it should be soil warms up. So, the specific heat largely controls the degree to which the soil warms up in the spring. It is a very important soil property, and the specific heat, remember that the specific heat of pure water is defined as 1 calorie per gram or 4.18 joules per gram, and that of a dry soil. So, the specific heat of dry soil is about 0.2 calorie per gram. So, you can see the specific heat of pure water is 5 times more than that of specific heat of a dry soil. So, as a result of that, wetter soils water soil warms more slowly than that of drier soils, because when there will be water in the soil, as a result of high heat specific heat, more amount of heat will be required to raise the temperature, and as a result of that the dry soil will will warm more faster than that of wet soil. So, this is the specific heat. And what is heat of vaporization? Well, it requires a large amount of energy, that is around 540 kilocalorie for every kilogram of water to be vaporized, and this use of energy for evaporation has a major effect because it cools the soil. So, what is thermal conductivity? It is very important aspect. Remember that the movement of heat in soil is also analogous to the movement of water. So, we have discussed about the movement of water in case of saturated soil, in case of unsaturated soil. In case of saturated soil, we will discuss about Darcy's law, and remember that. So, the movement of heat in the soil is analogous to the movement of water, and also the rate of flow being determined by a driving force and by the ease with which heat flows through the soil, and this can be expressed by Fourier's law. So, this is important, remember that this is called Fourier's law. Now, what Fourier's law says? The form of Fourier's law is QH equal to minus K into dt over dx, where QH is the thermal flux, K is the thermal conductivity of the soil, and dt over dx is the temperature gradient over distance x that serve as the driving force for the conduction of heat. So, this K is basically called the thermal conductivity. So, let us see some factors which affects the thermal conductivity of the soil. So, the first important factor is called compaction, because you can see the soil, when the soil is more compacted, obviously the heat flow will be more. So, obviously the arrow shows the heat transfer. As you can see, this is the loose soil, loosely aggregated soil, and this is the compacted soil, and the compact soil will transfer more heat, and compacted soil increases the particle, because this compact soil increases the particle contact, which helps in heat transfer. So, you can see here obviously in between the particle there are air molecules. So, as a result there is no particle contact, but as we are going from loose to compact soil, obviously there will be more particle to particle contact, and as a result of this particle contact there will be more heat transfer. So, compaction increases the heat flow in the soil. Another important aspect is the volumetric water content. So, you can see this is the interplay between volumetric water content, or in other words water content, with the thermal conductivity. So, as we are increasing the water content into the soil, thermal conductivity is also increases. So, if the water content of the soil is increased, it will also increase the heat transfer, and the water, because the water has more thermal conductivity than that of air. So, if the pore spaces are filled by water, they will obviously replace the air. The presence of water into the pore space will increase the thermal conductivity, because the water has more thermal conductivity than that of air. So, you can see there are two types of soil, one is aggregated loam and another is non-aggregated loam soil. So, in case of non-aggregated loam soil, or in other words it is a compacted soil, we can say. So, in case of compacted soil, obviously the thermal conductivity rise is more as compared to well aggregated loam, where there will be more amount of macropores. So, this is the implication of volumetric water content in thermal conductivity into in two types of aggregated soil. One is compacted, another is aggregated. And also temperature also shows variation with time and day. Obviously, soil surface temperature changes with the season, as you can see in this picture, and the subsoil temperature changes very little with the season, that is 4 to 5 meter depth, and subsoil temperature is less variable than that of air and surface soil temperature. So, the surface soil temperature changes more rapidly than that of subsoil temperature, because at the subsoil temperature is more or less almost constant. So, how you can control the soil temperature? Well, there are a couple of ways to control the soil temperature. Some examples of management strategies for controlling the soil temperature are organic mulches and plastic residue management. So, it generally used to buffer the soil temperature. So, as you can see in these two graphs, obviously this green this line shows the mulch condition, this is no mulch condition, and this is years. So, here also so days in January, the temperature in air is quite low. So, if we go for mulching, it will raise the temperature. So, it will protect the soil temperature from going below a certain temperature, so that the germination and biological activities and all other nutrient transformation can be maintained. So, similar the opposite can be found in case of August, because in case of August in case of drier months, obviously the air temperature will be higher, followed by the no mulch condition, and finally you will see lower temperature you will get in the mulch condition. So, it will conserve the temperature of the soil, and it will have, it will prevent the soil temperature to go beyond a certain limit, thereby preserving all the soil biological as well as physical and all the soil biological as well as chemical activities. So, this is the importance of mulch for soil temperature control. Remember that mulch from conservation tillage left the mulch for conservation tillage is also important, because in the definition of conservation tillage, it says the conservation tillage must leave the crop residues on the soil surface. So, when it leave the crop residues under the soil surface, it acts as a natural mulch or organic mulch, and it reduces the temperature, it reduces the transportation cost, and in other words it helps in maintaining the soil temperature, and obviously it is helpful in case of warm temperatures. Plastic mulches are used to increase the soil temperature. So, organic mulches in case of conservation tillage are helpful in warm climates, whereas plastic mulches are helpful in the cooler climate, because plastic mulches are used to increase the soil temperature in the cold region to and there are two types of plastic mulches. One is called clear plastic mulches, another is black plastic. So, clear plastic has greater heating effect than that of black plastic, and generally it is used to in cool climate for growing crops for pest management. The major disadvantage is that it is non-renewable, but some nowadays biodegradable plastic films can be used as a mulch. So, as you can see, these are some biodegradable plastic mulches farmers are using nowadays for mulching purpose in the cooler climate region. So, another important aspect is the soil with more water having 3 to 6 degree lower temperature than that of dry soil, and to get a warm soil obviously you need to improve the drainage condition. So, so obviously we have already discussed why the temperature in dry soil is higher than that of wetter soil. So, moisture control is also another factor to to control the soil temperature. So, guys, we have finished this soil temperature chapter. So, I hope that you have learned something new, and let us go and solve some problem in the next lecture, next tutorial. So, we will be solving 3 problems. Obviously, let us relating to soil aeration and soil temperature. So, let us start with problem 1. So, the problem says, consider a cropped field with an effective root zone depth of 80 centimeter, a daily so, the effective root zone here is 80 centimeter, a daily transpiration rate of 6 millimeter, and a daily soil respiration rate of 10 gram oxygen per square meter. So, calculate what fraction of the oxygen requirement is supplied by convection of if air is drawn from the atmosphere in immediate response to the pressure deficit created in the soil by the extraction of soil moisture. So, let us first calculate the volume of water that is being extracted per square meter. So, the volume of soil water that is being extracted per square meter by the crops through transpiration process is 1 square meter multiplied by 0.006 meter. So, because we are converting 6 millimeter to meter. So, we are getting around 6 liter per day. Second, you can see volume of air drawn from the atmosphere will be similar to the volume of water withdrawn from the soil, that is 6 liter, because whatever water the plants are drawing from the air, drawing from the soil, I am sorry, these water will get replenished by air from the atmosphere. The similar volume will be maintained. So, here volume of air drawn from the atmosphere will be similar volume to that the volume of water that is been withdrawn from the soil. So, volume of oxygen drawn from the atmosphere will be 6 multiplied by 21%, that is 1.26 liter, because we know in the atmosphere there are 21% of oxygen, And also so the mass of oxygen drawn from the atmosphere, if we convert it to the gram per liter, will get around 1.8 gram, and that comes from 1.26 over 2 into 2.4 multiplied by 32. So, how it comes? Because you know that 32 gram is the molecular weight of oxygen, 32 is the molecular weight of oxygen, and 22.4 liter is the volume of 1 mole of gas at standard temperature and pressure. So, basically we are converting this liter of oxygen to the to the gram. So, once we calculate this is 1.8 gram, the final question is we have to calculate what fraction of the oxygen requirement is supplied by convective air by convection if air is drawn from the atmosphere in immediate response. So, the percentage of daily oxygen requirement supplied by convection is 1.8, which you have already got, and 10 is the total is the daily soil respiration rate got from here percent. So, that will come around 18%. So, I hope that you have understood this solution. So, let us go ahead and see what is our next problem. Now, this also deals with soil aeration. So, this problem says that consider a soil profile in which the air phase oxygen concentration diminishes linearly from 21% at the soil surface to half of that at 100 centimeter depth. So, if the total porosity is a uniform 45% and the volume weightness is 35%, calculate the diffusion rate using Penman's coefficient for the effective diffusion coefficient of oxygen in the soil ds. Assume steady state diffusion and use a value of 1.89 into 10 to the power minus 1 square meter per second, square centimeter per second for the bulk air diffusion coefficient. Again, you have to consider that there is a soil profile and there is a steady state flow, and it linearly this oxygen concentration depletes from 21% at the soil surface to its half at 100 centimeter depth. They have given the total porosity of 45% and they have given volume weightness 35%. So, we have to calculate the diffusion rate using Penman's coefficient. Now, in the last lecture we have already discussed about the Fick's law of diffusion as well as their Penman's modification. So, we will be using that Penman's modification and Fick's law for solving this problem. So, our first step is to estimate the effective diffusion coefficient ds using Penman's linear relation between ds and the air field porosity Fa. So, if you remember, the Penman equation shows ds over d0 equal to 0.66 Fa, where 0.66 is the tortuosity factor. Now, we know that this Fa or air field porosity can be calculated by subtracting the volume weightness from the total porosity. Now, we know the total porosity is 0.05 and the volume weightness is 0.035, and basically the bulk diffusion air diffusion coefficient, the value is 0.189 square centimeter per second, which we got from here. So, ultimately we are getting 0.0126 square centimeter per second. This is ds. So, once we calculate ds, let us see what is our next step. So, we now use the Fick's law to calculate the steady state one dimensional diffusive flux Qd of oxygen through the soil profile from the atmosphere to the plane at which the oxygen concentration is 50% and the depth is 100 centimeter. So, let us use the Fick's first law. So, the Fick's first law is Qd equal to ds multiplied by dc by dx. Now, recall that the concentration of oxygen in the external atmosphere is about 0.32 multiplied by 32 gram per 22.4 liter. So, that comes around 3 into 10 to the power minus 4 gram per cubic centimeter. So, therefore, by substituting this number into this equation, we get a value of Qd, that is 1.26. So, we have already calculated this in the this ds value, we have already calculated this. So, the initial initial concentration of the external air is this, and the final concentration will be 50%. As you can see, the oxygen concentration is about 50% of the atmosphere. So, the final concentration is 1.5 multiplied by 10 to the power minus 4, because you know the dc is the changes in the concentration. So, we are getting in the changes of concentration from the atmosphere to the soil at 100 centimeter depth. So, here dx is 100. So, ultimately we are getting 1.89 multiplied by 10 to the power minus 8 gram per square centimeter into second. So, this quantity can be multiplied by 10 to the power 4 square centimeter by meter square and by 8.64 10 to the power 4 second per day to obtain the flux in gram per square meter of soil surface per day, because you know that in one day there will be this amount of taken. So, 8.64 multiplied by 10 to the power 4 seconds. So, you just need to convert this 1.89 into 10 to the power minus 8 gram per square centimeter second to flux in gram per square meter of soil surface per day. So, for getting that, we have to multiply these 1.89 into 10 to the power minus 8 with 10 to the power 4 into 8.64 multiplied by 10 to the power 4. So, we are getting a total a final value of 15.83 gram per square meter per day. So, this is our final solution. So, basically in this solution we are using first the Penman's equation to calculate the ds, and using the ds we will calculate the diffusion flux Qd using the Fick's law. And remember that here we have to calculate the diffusion gradient also, and this concentration gradient, and this concentration gradient can be calculated by subtracting the initial concentration of oxygen and the final concentration of oxygen. We know that final concentration is just half of the initial concentration, and the distance is given, it is 100 centimeter. So, once we get that, we have to just convert into gram per meter square using suitable multiplication factor. So, I hope that you have understood this solution. So, let us go ahead and see our third problem. So, in this problem it says that assuming steady state condition, calculate one dimensional thermal flask and total heat transfer through a 20 centimeter thick layer if the thermal conductivity is 3.6 into 10 to the power minus 3 calorie per centimeter second degree and a temperature differential of 10 degree centigrade maintained across the sample for 1 hour. So, here first, and we will be using Fourier's law for solving this problem, and as you can see we are basically calculating QH here, and this QH can be calculated by using this formula where K is the thermal conductivity and dT over dx is the temperature gradient, and you can see that the thermal conductivity value is already given, that is 3.6 multiplied by 10 to the power minus 3 calorie per centimeter second degree, and so we have to and here the temperature differential is already given, that is 10 degree centigrade. So, it is basically dt, this is k, and this is dx. So, dx we already know, that is 20 centimeter thick layer. So, ultimately we are getting 1.8 multiplied by 10 to the power minus 3 calorie per square centimeter second. So, we have to calculate it for 1 hour or 3600 second, because you know 1 hour equal to 3600 second. So, what we got, that's QH, you know, the total heat transfer is basically the multiplication of QH with the total number of seconds in 1 hour. So, ultimately we are getting 6.48 calorie per square centimeter. So, guys, these are couple of you know, problems and their solution. I thought that I should discuss with you uh, to give you, you know, to help you understand different soil physical process, especially soil temperature and soil aeration, and these will be helpful for you to in the near future for solving several related questions. Obviously, I cannot cover all the you know, different types of problems because of time constraint. However, I would you know, I would expect that you will go ahead and consult different text and reference books for solving and for consulting different types of problem related to the soil physics, soil physical parameters like soil layer, soil temperature, soil water, and soil porosity, and so on and so forth. So, by you know, by this we are wrapping up the soil physical processes, and from the lecture which will start next week, we will be starting the soil chemical process. So, if you have any question, please feel free to email and feel free to ask me any questions, and I will be more than happy to explain any queries you may have. Thank you very much.